everyone. The day has finally arrived where we are going to start talking about the graphs of trigonometric functions. Now, this was a lesson that should have been covered last year in Algebra 1A. You may or may not have seen it, depending on where we were at last year, but that's okay. This lesson by itself is a pretty easy one to grab onto. So what we're looking at today, we've been talking about trig functions on the graph of the unit circle, where the x, y coordinates really represent the sine and the cosine of a given angle. So we've been looking at the angles as we go around the circle, and then the x and y coordinates give us the sine and the cosine. What we want to be looking at today is, for example, this first one we're going to look at is the function y equals sine of x. So x, along our x-axis, is our angles. And then the output, what we would get for the sine value, is what's going to be showing up here along the y-axis. Okay, so that's going to give us a slightly different view of what's going on. Now, we are going to refer back to the unit circle, but really most of our work is going to be able to be done using just these four corner points that we use as kind of landmarks. And I'll refer to some of the other angles as well, but you really can draw this graph just using these 4 points on the unit circle. Okay, so to back up a second, the sine, cosine, and tangent functions, really all trig functions, are what we call periodic functions. Periodic means that they cycle or they repeat, and you'll see that. You probably have an idea of that just from the fact that we can go around the unit circle over and over again, but you'll see in the function what we mean by a periodic or repeating, a cycling function here. So I want to think about these 4 points, and I'm thinking about them in radians. So in radians, we know this is 0 and this is pi, right? Which makes this pi over 2, and this is 3 pi over 2. And then I want to think about the sine values. Now remember, the sine values are the y coordinates. So if I think about the coordinate, oops, I wrote that backwards. Sorry about that. This coordinate would be 1, 0. This coordinate would be 0, 1. This is -1, 0, and then this is 0, -1. And for this first one, I'm specifically looking at the sine, which is the y coordinate, right? So I'm looking at this value here. And notice it goes from 0 to 1 to 0 to -1, okay? And so here's what we're going to do. At 0 radians, I'm reading from here that my sine value is 0. So we're going to put a point right at 0, 0, because the sine of 0 is 0. When I get to pi over 2, my sine value is a 1. When I go over to pi, my sine value is back down at 0. And then when I go to 3 pi over 2, my sine value is -1. Now, what would happen if I went to 2 pi? Well, 2 pi would be back over here again, right? And so at 2 pi, my sine value would be 0. And so let's think about what would happen if we kept going. 5 pi over 2 is really just the same as 1 pi over 2, right? Because this would be like 4 pi over 2. So there's 5 pi over 2. So my sine value there is a 1. Okay. If I went on to 3 pi, that would be the same as 1 pi. Okay. It's just 1 pi after you've gone around the circle one full time. And so my sine value is back at 0. And so you get this curve that kind of goes up and down and up and down again. Okay, and that pattern is just going to repeat over and over again. Well, what about negative pi over 2? Where would that be located? Well, if I'm standing here, negative pi over 2 is the same as 3 pi over 2, right? And that had a sine value of -1. Negative pi, it would be here, and that's the same as positive pi with a sine of 0. And then you can probably figure out what's going to happen from there. This one would be here, and that would be a 1. -2 pi is going to be back around where we started, and that's going to be back at 0. And so on. We can kind of just fill in the rest of this. And so my sine function is going to look something like this. Now, you do want to be careful, and I try not to get too nitpicky about this, but these should not be like straight lines with pointy edges, okay? This is supposed to be kind of a smooth curve. And if you look at like the sine values, if I looked at all the y coordinates in this first quadrant, they'd start down here at 0 and they'd be getting larger and larger and larger and larger until they hit 1. Okay, and then they'd be getting smaller and smaller and smaller again, because remember, we're talking about y coordinates on this graph. And so as I move up the circle, my y-coordinates are getting larger because I'm getting higher, okay? And then as I come back down, my y-coordinates are falling again. Down here, my y-coordinates are all going to be negative, and that's what we see happening here. They're getting larger, they're getting smaller, they're dipping into negatives, and they're coming back to 0, okay? So this is the graph of the sine function. Now we're going to talk about some properties of this graph, okay? First of all, the domain. The domain is what are we allowed to put in here for x? What values is x allowed to be? And I didn't see anywhere where I had to stop my graph and say, wait a second, we can't put that number in here. Okay, we do typically number these graphs a little bit differently, but really we could find any number we wanted along this x-axis if I wanted to. So my domain is all real numbers. For my range, we want to think about what's the lowest point and the highest point on the graph. And you'll notice these never dip below -1 and they never go above +1. So my range looks like this: -1, less than or equal to y, less than or equal to +1. And that makes sense on the unit circle too, right? That your smallest sine value is going to be -1, your largest is going to be +1. We don't have any values up here or down here, right? Everything stays kind of contained within that radius of 1. Okay, the period, and this term might be new to you in the context of this function. This relates back to the fact that we call this a periodic function. Remember, a periodic function is one that cycles or repeats, and so the period of the function is talking about how long along the x-axis does it take for one full cycle to be completed, okay? So if I start here at 0, and I go up and I come back down. Now I know it's tempting to think like, oh, we got back to where we started, right? But this is not a repeat of what we just did a second ago. However, if I stop here, I went up, I came down, and then this is where I'm like starting over and starting this same pattern again, okay? So it took me from 0 all the way to 2 pi to run one full cycle of the graph. If I picked up that portion of the graph right there, if I cut it out and picked it up and laid it down on another portion of the graph, it would repeat itself over and over and over again. That's what the period is how much of the graph do I need to repeat the cycle over and over. And that should make perfect sense to you because it takes a rotation of 2 pi to get back to the beginning on the unit circle. Okay, so it should make perfect sense that the period is 2 pi because that's how long it takes the sine values to start repeating. Okay, the y-intercept here is located at 0 because the sine is 0 at 0. So the y-intercept is always at 0 for the sine function. Let's look at where our x-intercepts are located. So we have an x-intercept at 0, we have an x-intercept at pi, we have an x-intercept at 2 pi and 3 pi and -pi and -2 pi. So if you think back to when we were working with singularities, we had a name for all of those points. We called them the multiples of pi. And I'm perfectly fine if you just write that as your answer, that your x-intercepts are located at multiples of pi. I do want to show you another way that these are sometimes written. When we're talking more mathematically, like algebraically on a graph, we sometimes say x equals pi times n, which is really just saying multiples of pi. So this n could be a 2 or a 3 or a -5, and that represents all those multiples of pi. Okay, maximum and minimum is kind of a redundant question. This is really asking the same thing that range did. The max is 1. And the minimum is -1. The symmetry of the graph, your book makes a really big deal about symmetry. Your book does a lot of relationships based on symmetry of graphs, and so that's why I want to make sure we talk about it, because I'm sure in the homework, excuse me, you're going to be asked some questions about that. This doesn't have symmetry where you can like pick the graph up and fold it in half. But it has what's called rotational symmetry. If I put my pen right here on the origin and I spin this graph 180 degrees, it would land back on itself. So we say this has rotational symmetry around the origin. And again, I don't find that to be a super critical concept right now, but I do know your book is going to ask about it. So you'll want to make sure you have it written down. And then last thing there is asymptotes, and that kind of goes back to this whole idea when we talked about the domain that there weren't any restrictions, right? There's no place that I'm restricted, so there's no asymptotes on this graph. The sine function has no asymptotes. There are no undefined values when we're talking about sine, okay? Spoiler alert, there aren't any for cosine either, and we learned about that when we talked about singularities when we were doing proofs. However, when we get to tangent, we'll talk about some asymptotes. Okay, so what I would love for you to do right now, the next page has us doing this exact same thing but with the cosine function. It would be a great idea if you paused the video right now and started sketching the cosine function graph on your own. Do it the same way we did. Start with this unit circle, except this time instead of focusing on the sine values, focus on the cosine values, which would be the x coordinates on the unit circle. So, like I said, I would pause the video right now, start sketching the graph, maybe do one full cycle, and then resume the video and see if yours matches mine. I'm going to start this the same way I did a second ago with a circle. And we know this is, well, I don't think I need to number the angles again, but I'll put the coordinates back down here. So 1, 0, 0, 1, negative 1, 0, and 0, negative 1. And this time I'm focusing on the cosine value, so I'm focusing on these x coordinates. So when I start at 0, radians here in the corner, my cosine value is actually a 1. So this time I'm starting up here, right? When I go up to pi over 2, my cosine value has become a 0. So at pi over 2, I'm down at 0. When I go to pi over here, my cosine is negative 1. And then at 3 pi over 2, I'm back at 0. Okay? And that's really one, well, I'm sorry, I shouldn't say one full cycle yet. One full cycle would be going all the way back to 2 pi, which is back at 1. So at 2 pi, I'm back up here. So this here represents one full cycle of the cosine graph. Notice that means the period of this thing is still going to be 2 pi because it's going to take a length from 0 to 2 pi to get this graph to repeat. If we went to 5 pi over 2, that would be back up here, and that's at 0. 3 pi would be the same as 1 pi, and that's at negative 1. So I can kind of finish out this curve here. Okay. Negative pi over 2 would be going from here backwards, so that would have me at 0. Negative pi is back around here at just 1 pi, right? Negative pi and positive pi land in the same spot. And so negative pi is at negative 1. Back here, negative 3 pi over 2 is back at 0. And negative 2 pi has me back at positive 1. And again, you can probably just fill in the pattern from here and see what this function is going to look like. And again, this should be kind of a smooth curve. And so really, this graph looks a lot like the sine function, okay? And that should make sense to us because those sines and cosines are repeating themselves all over the circle. This one's a little bit different in that we're talking about x values. So when we start with the cosine function, we're at the farthest x value we could find. As far as y values go, this is kind of the starting point at 0, right? And then we're moving up from there. But when I'm talking about x values, I'm already out at 1, and as I move this way, I'm actually getting smaller along the x-axis. Okay, so I'm moving from positive 1 backwards to negative 1, and that's what you see happening here. Positive 1, and then I'm shrinking until I hit negative 1. And then when I start around this bottom half of the circle, my x-coordinates are getting bigger again because I'm moving along the x-axis. So that's what you see happening here. Okay. So the sine function and the cosine function, really the graph looks exactly the same. They are translations of each other. And eventually we're going to explore exactly how much they're off by. You know, how far do I need to drag the sine function over to get it to line up with the cosine function or vice versa? Okay, so you're going to find that a lot of these properties are very similar to when we talked about the sine function. The domain is still all real numbers. Okay, because I don't have any discontinuities here. I don't have any place where my graph breaks off. Okay, my range, you'll notice my highest is still 1, my lowest is still negative 1. okay? The period, the cycle looks a little different, but still, if I break off this chunk of the graph from 0 to 2 pi, that represents one full cycle, okay? So that's the period of the graph, is the length it takes to get from the starting point to where it starts to repeat. By the way, you can also think of the period as being the distance between like one bump and the next bump. So if I go from here to here, that represents a distance of 2 pi, okay? Also, if I was to go from here to here, so from negative pi to positive pi, that is still a length of 2 pi, okay? So the period is how long does it take for the graph to start repeating itself? It's usually easiest to start at 0, but you could really grab any two places on the graph that kind of correspond with one another and find the distance between them, and that'll give you the period. All right, notice my y-intercept has changed. So this time, instead of starting at 0, I'm starting at 1. And this is probably the defining feature that when I'm looking at a graph and I'm trying to decide if it's sine or cosine, this is what I look for. Is sine starts up here at 1. I'm sorry, cosine starts up here at 1. Sine starts here at 0. And so if I just hand you a graph and I don't tell you if it's sine or cosine, that's how you can tell the difference between the two. Your x-intercepts here, notice where they're at, pi over 2, 3 pi over 2, 5 pi over 2. If we went on, it would be 7 pi over 2. Those are your old friends, the odd multiples of pi over 2. And again, I'm fine with you using that same language we used when we talked singularities. You might also see them written this way. The first x-intercept is at pi over 2, okay? And then if we add pi to that, however many times, it'll get us to the next x-intercept. So pi over 2 to 3 pi over 2, that's a distance of 1 pi between the two of them. So this is really just saying you can hop along the x-axis by multiples of pi and land on your next intercept. Okay, max and min, same thing. So the max is 1, min is negative 1. Symmetry. Now this one does not have the rotational symmetry that the sine function did. This has the symmetry that you're probably more accustomed to. I can take this graph and fold it in half right down the y-axis. Okay, so this has what's called reflection symmetry, which again is probably what comes to mind more often when you think symmetry. Over the y-axis. And for asymptotes, like I mentioned before, there are none for sine or cosine. There are no discontinuities. There's no angles that cause us any problems when we're just talking about the cosine function. Okay, for the tangent function, I know I left you a space for you to draw it, and you can just kind of sketch it based on what I'm about to show you. I am less concerned with you being able to draw the tangent function by hand. More concerned with you understanding what's going on with the tangent function, because the tangent looks very different from sine and cosine. Okay, sine and cosine are these nice, numbers that fall in this pattern from the circle. Tangent is a relationship between sine and cosine, and so that makes it look very, very different. So what I'm going to do is I'm going to use Desmos to graph this one, and then we will talk about how to fill in all of those values. And so like I said, I'm not so worried about you understanding how to graph this by hand. Okay, this is what the tangent function looks like. So you'll notice I just typed in tangent of x. I've got my graph set up to be numbered similarly to how your graphs are on your notes. And we get these crazy like curve things with the cosine or with the tangent function. So I think what I will do, be patient with me here a second. I'm going to try to split screen a little bit. Do this, and we'll do this. I don't want to squeeze this too much. Maybe we will make this just go from negative 2 pi. Okay. So what is really important about the tangent function, besides just the fact that it's shaped differently, I'm going to move this so we're just kind of looking at that first chunk there, is there are asymptotes here. So if I drew a vertical line right here at pi over 2, and actually maybe let me do that real quick. X equals pi over 2. And I'm going to set that to be a dotted line so that you understand it's an asymptote. And I could go in and I could draw the others too. So I could draw the next asymptote over. I'm not going to. I'm just going to stick with that one. You'll notice this dotted line represents an asymptote. And that asymptote shows up over and over and over again. So we have another asymptote here at 3 pi over 2. We have one at negative pi over 2. That should not be a surprise to you, because we talked about how tangent is undefined at pi over 2 and 3 pi over 2 and 5 pi over 2. Tangent is undefined at those odd multiples of pi over 2 because that's where the cosine is equal to 0. So just real quick, if I throw the cosine graph on here, you'll notice, so that green curve represents the cosine function. Anywhere the cosine hits 0, the tangent is suddenly undefined, because remember, tangent is sine over cosine. Okay, so everywhere, every one of those x-intercepts, when we talked about the cosine function and we said these were our x-intercepts here at odd multiples of pi over 2, that immediately means those are going to be asymptotes of the tangent function. Okay, because tangent is sine over cosine, and you can't have that 0, which is what is happening at an x-intercept, right? You can't have that 0 on the bottom of a function. Okay, so let me unmess our graph here a little bit and get rid of that cosine function there, and let's talk about some of the properties we see. So the domain for this one, we have to be careful because it still stretches out forever left and right, but it does have some restrictions. So I want to say all real numbers except, and then again, you can write this a couple different ways, but probably the way you're most familiar with is just calling them the odd multiples of pi over 2. So I can put any x value in except for those places where the asymptotes show up. Okay? Now, as far as range goes, you will notice that these graphs go up and they go down forever. Okay, there is no restriction on the tangent function's range, so the range is just all real numbers, as opposed to sine and cosine, which are really limited between between -1 and +1. And we talked about that a little bit too in the last chunk of this material. We talked about how tangent is allowed to be larger than 1, but sine and cosine are not. Okay, the period of this function, how far does it take before this function repeats itself? And so really, if I look at, like, for example, this x-intercept here to this x-intercept here, that would kind of represent one full cycle of this graph. Notice that this function repeats itself every pi along the x-axis instead of every 2 pi. So it repeats more often, okay? You could also look at it as like from pi over 2 to 3 pi over 2. That is a distance of 1 pi. And so this one red line right here represents one full cycle of the graph. Or maybe it's easier to think about it as like negative pi over 2 to positive pi over 2. Let me do this real quick. Just putting that other asymptote in there. Let's also make that a dotted line. Okay, so if I look at the distance between the purple line and the blue line, the two dotted lines, that is a distance of 1 pi, and it erased my markings here, but this is negative pi over 2, this is positive pi over 2. Put those together and you get 1 pi, and so this one red line here represents one full cycle. So the period of this function is just pi, okay? Another way I could illustrate that, we talked about this a little bit in the last section, is remember your tangents are positive here, negative here, positive here, negative here. So when I go from this point to this point, my tangents start repeating themselves. I only have to go halfway around the circle to get them to repeat, as opposed to sine and cosine where you have to go all the way around the circle. Okay, so just another justification for why the tangent has a period of pi. Y-intercept is at 0. Your x-intercepts here are located, and I'm going to click here, so this one is pi, This one is, let me put this away for a second. You've got one x-intercept at pi, you've got an x-intercept at 2 pi, you've got an x-intercept at negative pi, okay? Those are the multiples of pi. And again, and I keep saying this, but maybe I should write this here. We talked about how the cosine being 0 is what leads to those asymptotes. So the cosine is 0 at these dotted lines, and we kind of showed that, right? Oh, I took it out of here, but we put our cosine function in here. And when I did, you'll notice that the cosine hit 0 at every one of those asymptotes, because anywhere cosine is 0, my function is going to be undefined. I'm going to have a 0 here. The tangent is going to equal 0 anytime the sine equals 0, right? Because if I have a 0 on the top of a fraction, it's just going to equal 0. So watch what happens if I make this the sine function instead of the cosine function. Okay? You'll notice that these two things share their x-intercepts. The sine function shares its x-intercepts with the tangent function, because anytime sine is equal to 0, tangent's going to be equal to 0 as well. Okay? Maximum, minimum, there are none. And again, that relates back to the fact that your range can be anything. So your tangent function goes up and down forever. This has that same rotational symmetry as the sine function. So it really shares a lot of properties with sine, and that has to do with the fact that sine is on the top of the fraction. So rotational symmetry around the origin. And the asymptotes are located at those odd multiples of pi over 2. Didn't we put that somewhere? Oh, yeah, up in the domain. So the asymptotes are located at x equals, and I'm going to write it kind of that fancy way. So pi over 2 plus pi n. But if you were just saying it in words and you just said, you know, the asymptotes are located at odd multiples pi over 2, that's okay with me. Okay, this is just more of an algebraic way to express this. And again, this is just saying that my first asymptote is at pi over 2, and then if I take a leap by pi to my next one, that's where my next asymptote is going to show up. So if you would like to sketch just a quick picture of the tangent function, let me get rid of some of this other grossness here. Just so you have a visual in your notes, that's perfectly fine. Like I said, I probably will never ask you to draw this one by hand, but you will have to understand especially the asymptote piece of the tangent function. That's really important. And that's not new. We're just looking at it in a different way now. That's really it for this lesson. Your homework for today really just focuses on these properties of the different sine, cosine, and tangent functions. You're not going to have to do a lot of math. You're just going to have to understand what these graphs look like. So give that a try, and we will talk about it together next class. Have a good one.